Hello everyone, and welcome to Precipitation Reactions. And so in the previous video, I gave a few examples that had to do with aqueous solutions being mixed together and you resulted in a product that became a solid. And so in those particular cases, those are what we refer to as precipitation reactions. And so precipitation reaction occurs when you have two solutions that contain aqueous substances. Again, aqueous, 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 aqueous. If you mix those two solutions together, you end up forming a solid or an insoluble product. And so insoluble product basically just means that these ions are no longer freely floating around. They have come together, they have made a nice bond, and they just can't exist in water anymore. And so they end up forming a solid and being removed from the water. And so in these cases, you can call these reactions metathesis reactions, but a warning I have to give you about the idea of double displacement reactions. So the term double displacement is a very, very wide and broad category that encompasses a lot of different types of reactions. So precipitation reactions, they are double displacement reactions. But so are acid-base reactions, some redox reactions, and other types of reactions fall into this category. And so more specifically, if you mix two aqueous solutions and end up with a solid, you have formed a metathesis or a precipitation reaction. Do not describe that as double displacement because that is way too broad. So, soluble versus insoluble. What the heck does that mean? So a soluble substance, as I've kind of covered a couple times, will completely separate into its individual components. And so something like sodium chloride. If you take solid sodium chloride and place it into water, you are going to end up with sodium ions and chloride ions. If you take something like silver nitrate and you place it into water, this stuff will completely break apart and you will end up with silver ions and nitrate ions. Please notice, there is no silver nitrate left inside this beaker. There is no such thing as AgNO3 completely intact in water. You are going to have complete dissociation, complete separation of these silver ions and these nitrate polyatomic ions. In addition to that, please note that NO3 still stays NO3. You're not going to have any separation of the nitrogen from its oxygens. Those still need to be treated as a single entity or as a single network of atoms, if you will. On the other hand, if you were to mix silver nitrate and sodium chloride into the same beaker, you would then have some chlorine ions and silver ions that will, essentially join forces, and because of that, they're kicked out of water. And so something like silver chloride is insoluble in water. And so silver chloride will form a solid, or if you drop silver chloride into water, it will remain a solid and just drop down, straight down to the beaker, remaining completely intact silver chloride. And so there are some rules that you need to know about. And so I'm telling you right now, because you're watching this as a YouTube video, pause the video, go get a drink of water, take a deep breath, and then hit unpause as soon as you are comfortable and ready. Life is okay. You will be fine. So, welcome back from your break. Now, look at this horrible table. It is long, it does have a lot of words, but I promise you it's not as difficult as you are trying to make it as you're looking at it right now. And so there's basically 7 rules that you need to pay attention to. Those 7 rules are, I'm saying 7 because I'm going to group this first 3 rows here into one group. But if you do not memorize all of them, which you should because I even have it in red letters, know all of these. So I do highly suggest you memorizing all this stuff. But if you refuse to listen to me and you refuse to know all of them, at least know these first 3, or what I'm going to call the first rule. And so if it contains anything from group 1, which would be lithium, sodium, potassium, rubidium, cesium, francium. Well, no, not francium. Francium doesn't react. But lithium, sodium, potassium, rubidium, cesium. Or if it contains an ammonium ion. Or if it contains a nitrate, or an acetate, or a perchlorate. If it includes any of these, that's it. End of story. There are no exceptions. That thing is always 100% going to be soluble. So if it contains anything from group 1, ammonium ion, nitrate, acetate, or perchlorate ion, polyatomic ions, then again, it is going to be soluble. If it contains a chloride, a bromide, or an iodide, and again, normally, if it contains chloride, bromide, and iodine, it is going to be a soluble substance, unless it has one of these exceptions. And so if you have a chloride, bromide, and iodide, and it's attached to a silver plus, a lead 2 plus, a copper plus, or this very weird looking mercury 2 plus, then it's going to become insoluble. And so something like sodium chloride, soluble. If you have something like cesium chloride, soluble. If you have iron chloride, soluble. But if you have silver chloride, silver is one of those exceptions. It just basically nullifies all the rules that I'm telling you here, and this becomes insoluble. Same deal with silver bromide or silver iodide. One special thing that I need you to take special note of is this is a lead 2 plus ion. And so in this case, if it is PbCl2, that is going to be insoluble. But if you have a lead 4 plus ion, or in case PbCl4, that is going to be soluble. And so these exceptions are very specific on what ions they are talking about. So please note it has to be a lead 2 plus. It has to be a mercury 2 plus. And if it's not, then again, it's going to be soluble. Fluorides are very similar in the case that most fluorides are going to be soluble, unless it's anything from group 2. And lead 2 plus, sorry. And so lead 2 plus with a fluoride, or calcium, strontium, barium, any of those, you're going to end up flipping that fluoride and it's going to become an insoluble substance. Sulfate, very similar to the fluoride. If you have calcium, strontium, or barium, those are in group 2. Or if it has a silver plus or a lead 2 plus, hey, those are the same exceptions up there. And so in this case, a lot of these exceptions kind of overlap. So as I stated earlier, not as horrible as it looks because you really only have to know silver, lead, copper, mercury, but then again, silver is there and lead's there. Group 2s for fluorides, 3 of those group 2s are also for sulfates. And so, same idea, but the other way around. If it contains a hydroxide, typically you're going to be looking at insoluble substance. But if you have a hydroxide with group 1, which, hey, there's no exceptions for group 1, so this has to be soluble. Or if you have a hydroxide with calcium, strontium, or barium, those are the exact same exceptions for the ones up here. And so again, most hydroxides are insoluble unless they contain group 1 or calcium, strontium, or barium. Carbonates, phosphates follow the same rule. Carbonates and phosphates, if you have group 1A, which again, no exceptions. If you have NH4, because again, still no exceptions. And so the only real exceptions for the phosphates or carbonates is the exceptions that have actually no rules or exceptions up here. And the last one is sulfides. Same deal. Group 1A because that. NH4 because that. Group 2A, same exact reason here. And so, please note, sulfates are normally soluble. Sulfides, just an S by itself with a 2 minus charge, just a sulfide is going to be insoluble. So now you may be asking yourself, why does this all matter? Because of this. So if I give you some type of chemical reaction, now that you know how to do all this stuff, I'm not going to give you that entire chemical equation. Even on an exam or on a quiz or homework, I might not even give you these chemical symbols. I would probably just say something like potassium iodide is mixed with lead 2 nitrate, and you should be able to go from words into these letters. And so once you do that, or once you have at least bare minimum this, now you have to ask yourself, what are the letters I'm going to write after this? What are the states of matter? And so if you have potassium iodide, this is going to be either soluble or insoluble. So you have to look at your rules, and you notice 2 of these rules actually show up on that table. The first one is potassium, group 1, never going to be insoluble. In addition to that, iodide is normally soluble. Potassium is definitely not going to be one of those exceptions, so we know our potassium iodide is going to be aqueous, or it's going to be soluble substance. On the other hand, we have our lead 2 nitrate. And so nitrates, no exceptions. And so this thing has to be soluble. There is no particular rule with lead 2 plus unless you're talking about the exception portion. And so what I would suggest you actually learn from that previous table, know the exceptions, know what exceptions to each of one of those rules. And so if we have a solution of potassium iodide, no Ki is left over in that water. You have potassium ions and iodide ions. Same deal with the lead 2 nitrate. Once you place this into water, you're going to produce 1 lead 2 plus for every 2 of your nitrate ions. But please note, still no PbNO32 left inside of there intact. But as soon as we mix these two together, and please notice how I phrased the sentence, for a very split second, actually probably less than a split second, as soon as these two solutions are mixed with one another, you have a beaker that contains 4 ions. And so, real quick kind of backtrack here. Potassium and iodide, they already had their run. When they're on solid land, they get along great. They love sticking to each other. But as soon as you take potassium iodide and place it into water, they get ripped apart. They really don't have any incentive to kind of join back up with one another. So the potassium and the iodide, they already tried. They're done with that relationship. They will not join back up. Your lead 2 nitrate, same situation. On land, they're perfectly fine. But as soon as you put them into water, they kind of want to go their separate ways. They don't want to join back up. And so in this case, your limits or your options of what are going to be products are kind of getting diminished here. So we know lead 2 plus is not going to join up with the nitrate. And this potassium is not going to join back up with this iodide. And we also know potassium and lead 2 plus, they're not going to form a bond because now you're looking at 2 cations. This just doesn't work out very well. Same deal with these 2 anions. Not going to work very well. And so we kind of limited our options of what our products can be. So this is where we get the term double displacement. And so whenever you have a reaction in this case, basically the only option you have is to swap your partners. And so here, your potassium from the potassium iodide is going to go over here and react with this nitrate from the lead 2 nitrate. And the lead 2 plus from your lead 2 nitrate is going to go over and interact with the iodide from the potassium iodide. And so here, once you swap their partners, you have 2 products. Both of those or neither of those or one of those can have the potential of being a solid product. So the first thing you need to do is identify which ones do we have and then figure out if it's going to be a solid or if it's going to be a soluble. And so here, as I stated, your potassium and your nitrate are going to join forces to become KNO3. Your lead and your iodide can join together and they become your lead 2 iodide. Please note, one thing I kind of glanced over on the previous one, the main reason why this is PbNO3 is because we have a Pb2 plus charge. That doesn't change when you go from this side of the reaction to the other side. This lead 2 plus is still a lead 2 plus. And so you need to make sure that iodine actually has 2 of your iodines for every 1 of your lead 2 pluses. So please make sure, just because you're swapping the partners, even though according to this how it's drawn, you have 1 lead and 1 iodine, you need to make sure your chemical reactions and your chemical formulas are still written out correctly. So back to where we're going. KNO3, soluble or insoluble. And so this one is actually soluble. I call it a double whammy, because your potassium's never going to be insoluble. Same deal with your nitrates, never ever going to be insoluble. And so these things are always 100% of the time, potassiums and nitrates, always soluble. And then iodides. And so your lead 2 iodide. Iodine is normally going to be soluble, but lead 2 plus happens to be one of those exceptions. And so your lead 2 iodide is insoluble. And so here you would write out your KNO3 as aqueous, and you would write out your PbI2 as a solid. And so, in order to give you a more, pictorial view of this, if you mix aqueous potassium iodide, which you can see in this picture is clear, into lead 2 nitrate, which you can see again is clear. as soon as they come into contact with one another, or as soon as the iodine from the potassium iodide and the lead from the lead 2 nitrate come into contact with one another, they form potassium iodide. So you have a soluble substance plus another soluble substance that creates a soluble substance, and then something that is no longer soluble. Lead to iodide, the solute interactions between the iodines and the lead are much stronger than the solute-solvent interactions between the lead to iodide and the water. So in that case, lead to iodide does not get shredded apart. It stays completely intact, but at that point, water gets mad because it couldn't rip it apart. It says, all right, well, you can't stay here anymore, and so it kicks it out of the water. And so in this case, this lead 2 iodide will keep forming as long as you keep adding your potassium iodide, and after which time it will probably settle down to the bottom of this beaker, and you can either filter it away or centrifuge it or whatever you do in order to get to your solid. So, one thing that may seem kind of odd, and I'm going to give you a heads up before I change my slide here, is sometimes if you mix a soluble substance with a soluble substance, you could end up with soluble substances, in which case we would call this no reaction. And so, if we mix potassium iodide and sodium chloride together, you would have the double displacement reaction of your potassium going over to the chlorine and the sodium coming over to the iodine. In which case, potassium chloride, potassium always soluble, so potassium chloride has to be soluble as well. Sodium always soluble, so sodium iodide had no chance. Sodium was definitely going to win that battle, and so sodium will never become soluble. So you basically mixed water with water and ended up with water. And so inside of this beaker, yeah, you have a bunch of ions, but all they're doing is floating around. And so in these situations, you just have a beaker of floaters, but none of those floaties want to do anything else with anybody else, and so they just sit there and float all eternity until you do something else with them.